Hello friends, I am Rahul and welcome to my channel The Truth of Physics. Today we will discuss the rocket propulsion, and in this video I will derive the equation for rocket propulsion. In a rocket, the fuel burns and produces gases. These gases are ejecting outward like this from a nozzle, small nozzle at the end of this rocket. So these gases at high temperature, these ejecting gases at high temperature produces a upward thrust to this rocket, and for this the rocket got an acceleration and it starts to move in a upward direction. Now suppose at time t equals to 0, the rocket and fuel system, the mass of the rocket fuel system is m0 at t equals to 0. Now as time increases, the fuel burns and the mass of this rocket becomes smaller and smaller as time passes. So suppose we are considering a particular time, suppose t, small t. In this particular time, at this particular time, some amount of fuel is burnt and produces gases. These gases are ejected in the air, and so the mass of the whole system has decreased. So we are considering this time t, small t. So at this time, what will be the total mass of the system? The mass of the total system will be at time t equals to m, suppose m equals to m0, the mass, the initial mass of the whole system, minus the ejected fuel, where this represents the decrease of mass by the ejected gas or by the burnt fuel, where r is the constant rate of ejecting gas, that is r is minus dm by dt. So RT is the amount of ejected gas at time small t. Now suppose at this time small t, the velocity of this rocket is small v and the velocity of the gas ejecting outward with respect to this rocket is small u. So the linear momentum of this rocket and fuel system at time small t is p equals to m into v, that is m0 minus RT into v. Now consider a small time interval del t. So in this time interval del t, a mass del m equals to r del t. This amount of mass is lost by as the ejected gas, that is the mass of the ejected gas is del m equals to r del t at this time interval del t. So and suppose the velocity of this rocket has increased at this time interval del t del v. Okay, this is the increase in velocity of this rocket. Now what will be the momentum of the total system, that is the momentum of the linear momentum of this total system at t plus del t, at this time t plus del t. The momentum, suppose we have written this as p dash, will be equal to m minus del m, that is mass decrease of the rocket, into the velocity of this rocket v plus del v, as v was the initial, that is v was the velocity of the rocket at time t, and at time del t it has increased the amount del v. So now at t plus del t the amount will be, the amount of velocity of the rocket will be v plus del v. So this is the momentum of the rocket, okay, plus the momentum of the ejecting gas. So what will be that? The mass of the ejecting gas will be this del m, mass of the ejecting gas del m into the velocity of the ejecting gas. But we have considered the velocity of the rocket v with respect to ground, that is v, what we have written v, this is measured from the ground, with respect to the ground. But the velocity of the gas, that is u, we have considered with respect to the rocket. So what will be so we have to here write the velocity of the ejecting gas with respect to the ground. So what will be that? Suppose we can understand this by a simple thing. Suppose here is a static observer who is observing this situation, the rocket propulsion. So you will see that the rocket is moving upward with a velocity v, and the person in this rocket will see the gases ejecting outward at a speed u, that is this is the speed, this is the velocity of the ejecting gas with respect to this rocket. So this static observer will see to this static observer the velocity of the ejecting gas will be simply v minus u. This can be easily, you can easily understand this from the basics of vector. So the velocity of the ejecting fuel or the velocity of the ejecting gas with respect to the ground, here we have considered the static observer, that is this is nothing but the ground, okay, the static observer means the ground. So the velocity of the gas with respect to ground is v minus u. So this will be our momentum, the momentum of the whole system at the time t plus del t. So as there is no, we are considering there is no external force acting on this rocket fuel system, so we can apply here the conservation of linear momentum as there is no external force in this system. So this will be equal to nothing but the mass of the whole system at the previous mass of the whole system at what time? At the time t, that is m small v. This is our this is mv is the momentum, the linear momentum of the whole system at the time t, and this is the left hand side, this is the momentum of the whole system at time t plus del t. As the linear momentum is conserved, so the momentum before of the system will be equal to the momentum later of the system. We will get, if you calculate this will become del v m del m minus del mv, and del mv will be cancelled out, and mv and this mv will be cancelled out. So this will equal to v, this is equal to, and this will get in this side u del m. So del v will be equal to u del m by m minus del m. So this will be equal to del v equals to u, and del m is equal to r del t, m minus r del t. So if we divide this expression with del t, so this del t will be cancelled out. And if del t tends to 0, so we know that from the concept of differentiation, when del t tends to 0, del v by del t will become dv by dt, that is the derivative. And here when del t will be tends to 0, this term r del t will be 0. So this will equal to u r by m. And what is m? M we have discussed previously. M is equal to m0 minus r t. So this is m0 minus r t u r. So if you integrate this, dv integrate u r dt by m0 minus r t. Suppose we are considering from time t equals to 0. So at time t equals to 0, the velocity of the rocket was what? The velocity of the rocket was 0. So this will be the limit, lower limit at time t equal to 0, and upper limit will be suppose small t, time t. And suppose at time small t, the velocity of the rocket will be v. So here the limit is v, and initially it was 0. So if we integrate this, the left hand side will be, and putting the value of the integral, the left hand side will be v, small v, and the right hand side when you calculate will be equal to, the ur will be taken outside, and the value of the integral will be ln m0 minus rt limit from 0 to t, and here will be into minus 1 by r. This will be equal to minus u ln m0 minus rt by m0 when we put the limit. And if we take the minus sign inside the ln, so this will be equal to v equals to u ln m0 by m0 minus rt. So this is our equation of rocket propulsion. So if you really like this video, so please like, and if you have any doubt in this topic, so you can also comment below, and subscribe my channel and hit the bell icon for the latest notifications of my videos.